Good day, my name is Yanglin, and today I'm going to talk about privacy and correctness trade-offs for quantum homomorphic encryption. The talk is mainly based on the following preprint on arXiv. This is the outline of my talk. I will first introduce the motivation and then two important ingredients of my talk, that is quantum homomorphic encryption and quantum oblivious transfer. Then I will explain the reduction from quantum oblivious transfer to quantum homomorphic encryption. With the reduction, we can translate bonds from quantum oblivious transfer to quantum homomorphic encryption. Homomorphic encryption is a secure two-party computation protocol, which allows the server to compute on encrypted data of a client without first decrypting it. This figure illustrates the scheme of a homomorphic encryption protocol. Alice, the client, encrypts her data and sends it to Bob, the server. Bob computes a function directly on the encrypted data and then sends it back to Alice. And Alice then decrypts the encrypted data and directly obtains the output of the function. Considerable attention has been paid to homomorphic encryption since its proposal. Homomorphic encryption is sometimes called a Swiss Army knife primitive of classical cryptography because a broad class of cryptographic primitives can be constructed with homomorphic encryption as a black box primitive. Such cryptographic primitives include secure two-party computation, private information retrieval, and zero-knowledge proofs. We say that we can reduce this primitive to homomorphic encryption when these primitives can be constructed with homomorphic encryption. The success of homomorphic encryption in classical cryptography motivates the exploration of homomorphic encryption in quantum cryptography. Many protocols for quantum homomorphic encryption, either computationally secure or information-theoretically secure, have been proposed. An example of the information-theoretic secure code allowing Clifford gates is constructed by randomly permuting quantum error correction codes, and it is proposed by Ouyang et al. It is natural to ask whether quantum homomorphic encryption is a Swiss Army knife protocol of quantum cryptography. This motivates us to reduce another quantum cryptographic primitive to quantum homomorphic encryption. Quantum oblivious transfer is an important cryptographic protocol which has been well studied. Although perfect quantum oblivious transfer does not exist, imperfect quantum oblivious transfer, in which both parties have limited abilities to cheat, have been proposed. In our work, we formally define theoretically secure QH quantum homomorphic encryption, and based on our definition, we reduce quantum oblivious transfer to quantum homomorphic encryption. In a quantum homomorphic encryption scheme, Alice, the client, has an input role of an unencrypted system, A. He wants to delegate some computation to Bob, the server. Alice first uses the key generation map to generate an encryption key. Then he uses the encryption map and the key to encrypt her input. We denote the encrypted system by hat A. After that, Alice sends her message to Bob. Bob uses the evaluation map to evaluate the quantum channel F from the set scriptF on Alice's encrypted message and sends the evaluated message hat O back to Alice. Alice then decrypts the evaluated message with the key and the decryption map and obtain the desired output state tau in the decrypted system O. Now we summarize elements of quantum homomorphic encryption here. The quantum homomorphic encryption is characterized by the set of channels that this quantum homomorphic encryption can delegate. The key generation, encryption, evaluation, and decryption map denoted by script F. Key gen, inc, eval, dec, respectively. For quantum homomorphic encryption to be meaningful, it needs to return the correct output. This means if we encrypt, evaluate a channel, decrypt, then it should be equivalent to directly apply the channel. This is quantified by a property known as correctness. A quantum homomorphic encryption protocol is epsilon correct if for every quantum channel that this quantum homomorphic encryption protocol allows to delegate, and for every Alice's input row and its purification psi prime, and for every key generated by the key generation map, we must have this inequality, which is the trace distance between this directly apply this quantum channel and apply this quantum homomorphic encryption protocol. Their trace distance should be smaller than epsilon. Quantum homomorphic encryption needs to protect an honest Alice's input when a malicious Bob strives to learn Alice's input. An honest Alice will use the key generation map to generate the key and encrypts her input with the encryption map and the key. And in that case, Bob should not distinguish what Alice's input if he only sees the encryption. From a malicious Bob's view, the state he receives is an average of the encryption and the distribution over all keys. Therefore, the indistinguishability can be expressed as the trace distance between averages of any two encrypted messages is bounded by epsilon d. Quantum homomorphic encryption needs to protect an honest Bob's circuit when a malicious Alice strives to learn Bob's circuit more than what an honest Alice's output indicates. This property is called circuit privacy. Here is a concrete example of what an honest Alice's output can indicate. Consider a protocol in which Alice inputs two numbers to a quantum homomorphic encryption scheme, and Bob performs arithmetic operations. If an honest Alice inputs 2, 2 and receives 4 as output, she will learn that Bob applies either addition or multiplication, but he doesn't know which operation Bob applies exactly. So this is what an honest Alice can learn from Bob's output. Now consider an active protocol. A malicious Alice can send a corrupted message #A while keeping a reference system R#A. An honest Bob will evaluate his quantum channel on the corrupted message and sends it back to Alice. A malicious Alice can gain some information about Bob's circuit from the corrupted message and the reference system. We will compare the above active protocol to the following ideal protocol to quantify the information leakage from Bob. Imagine that there is a trusted third party, Charlie, who keeps each party's secret confidential. Initially, Alice holds her input and her reference system. Alice can send her input to Charlie, and Bob can send his quantum channel he wants to apply to Charlie. And Charlie will perform the quantum channel on Alice's input. and send the result back to Alice. If Alice in the ideal protocol can simulate Alice in the actual protocol with the simulation map N, then Alice in the actual protocol does not know more than Alice in the ideal protocol, and we call it the quantum homomorphic encryption is circuit private. Now, here is the formal definition of circuit privacy. A quantum homomorphic encryption protocol is epsilon c circuit private if, for any psi, this corresponds to Alice's corrupted message in the actual protocol. There exists psi prime. This corresponds to Alice's input in the ideal protocol. And N, this corresponds to Alice's simulation map in the ideal protocol, such that for any quantum channel F that Bob would like to apply, the trace distance between the Alice's final state in the actual protocol and Alice's simulation state in the ideal protocol, their trace distance is bounded by epsilon c. Now, we introduce quantum Oblivious transfer, which is the other ingredient of our reduction. We introduce the standard Oblivious transfer, a variation of quantum Oblivious transfer. In this variation, Alice inputs a request bit I and Bob inputs two data bits, x0, x1. After rounds of communication, Alice outputs x hat or about, and Bob outputs accept or abort. Ideally, Alice learns and only learns xi from this protocol. Now we introduce the properties of quantum Oblivious transfer. The quantum Oblivious transfer is delta complete if, when both parties are honest, then both parties accept, and with a probability greater than 1 minus delta, Alice outputs xi. We say this quantum Oblivious transfer protocol is PA star sound against a cheating Alice. If, with a probability of less than PA star, a cheating Alice can guess hat x0, hat x1 for an honest Bob's two data bits x0, x1 correctly, and both parties accept the protocol with a probability less than PA star. And it is PB star sound against a cheating Bob if, with a probability less than PB star, a cheating Bob can guess hat I for an honest Alice request bit I correctly, and both parties accept. In a previous paper, a trade-off between soundness of quantum Oblivious transfer has been obtained. We extend their bound to include delta completeness and obtain this above bound. This bound becomes a trade-off between the completeness, the soundness against Alice, and soundness against Bob of quantum Oblivious transfer. In order to perform the reduction, we define a set of quantum channels. We call them the strong Oblivious transfer channels, Fx0, x1. We first apply to completely dephasing channels, denoted by D, on two qubits, and then apply to C0 gates if x0 does not equal to x1, and these two C0 gates equal to a swap gate. And finally, we apply a X gate on the second qubit if x0 equals 1, and we apply a completely depolarizing channel, denoted by P, on the first qubit. We will show that this strong oblivious transfer channels can apply quantum oblivious transfer. Let the input be cat I, cat 0. If x0 equals x1, we do not apply the swap gate. The output of the second qubit is x0, which equals to x1. If x0 does not equal to x1, we apply the swap gate, and the output of the second qubit is x0 plus I. If I equals 0, then it's x0. If I equals 1, then it's x0 plus 1, and it equals to x1. The strong oblivious transfer channels can be realized with only Cliffords and 4 bits of uniform local randomness. That is, the completely defacing channels can be realized by applying identity or Z-gate uniformly at random, and the completely depolarizing channel can be realized by applying identity, X-gate, Z-gate, ZX-gate uniformly at random. We call these Cliffords the strong oblivious transfer Cliffords, denoted by this Fx0, x1, R0, R1, R2, R3. Quantum homomorphic encryption that allows strong oblivious transfer channels can be reduced to quantum homomorphic encryption that allows only strong oblivious transfer Cliffords. Suppose that we have a quantum homomorphic encryption protocol that delegates the strong oblivious transfer channels, which is denoted by the shaded area of this figure. The quantum oblivious transfer protocol can be constructed as follows. Alice encrypts her request bit as kate I, kate 0 with the encryption map of quantum homomorphic encryption and sends it to Bob. Bob evaluates Fx0, x1 according to his data bits x0, x1 with the evaluation map of quantum homomorphic encryption and sends it back to Alice. Alice then decrypts with the decryption map of quantum homomorphic encryption and obtains a completely mixed state tensor product x hat state. The second qubit of the output gives hat x, which ought to be xi. The properties of the quantum homomorphic encryption protocol translate to the properties of the quantum oblivious transfer protocol. More specifically, if we have a quantum homomorphic encryption protocol that allows strong oblivious transfer channels or Cliffords with epsilon correctness, epsilon d data privacy, and epsilon c circuit privacy, then we can use this quantum homomorphic encryption protocol to execute a quantum oblivious transfer protocol with epsilon completeness 1/2 plus epsilon c soundness against Alice and 1/2 1 plus epsilon d soundness against a cheating Bob. We further make use of the bound for quantum oblivious transfer. A quantum oblivious transfer violating the previous bound does not exist, and thus a quantum homomorphic encryption protocol allowing strong oblivious transfer channels or Cliffords and violating this corresponding bound does not exist either. Hence, we obtain a bound for quantum homomorphic encryption that allows for strong oblivious transfer channels or Cliffords. This bound reveals a privacy and correctness trade-off of a broad class of quantum homomorphic encryption, including quantum homomorphic encryption that allows Cliffords. Here we summarize the bound we obtain for quantum homomorphic encryption that only allows strong oblivious transfer channels and with perfect correctness. This blue line corresponds to the lower bound obtained from the reduction. The shaded area corresponds to the impossible regions. 2 block points corresponds to the 2 reachable points by nowadays protocols. The square corresponds to the trivial protocol that Alice sends her plain text, and the diamond corresponds to Ouyang's code that allows Clifford's. So, in conclusion, we have 3 main contributions in our work. We introduced the formal definition of information-theoretically secure circuit privacy of quantum homomorphic encryption. We then reduced quantum oblivious transfer to quantum homomorphic encryption with this definition of circuit privacy. And we obtain the trade-offs between this privacy and correctness of a broad class of quantum homomorphic encryption, which includes quantum homomorphic encryption allowing Clifford gates. So much for today, and thanks for your attention. If you have any questions, you can contact me with this email address, and thank you.